As we begin our study of organic chemistry, we're going to focus on the fact that structure determines properties. This will include some review of general chemistry, and we'll start to look at some structural patterns. Now, in general chemistry, we started using the language of chemistry. We talked about atoms, we used various symbols. Now, in organic chemistry, we're going to continue with that and further develop the vocabulary of our language of chemistry. In this chapter, we're going to start with some review of atomic structure, followed by a review of compounds. And then we'll spend most of our time focusing on organic chemistry. We're going to start with a focus on structural details that we're going to continue to use throughout the year to understand the properties of organic compounds. So here we have some of the symbols that we've seen before. Now let's look at this one in particular. First of all, what is the C? This is the chemical symbol for the element carbon. What is the number 6? This refers to the atomic number. This gives us information on the number of protons or the number of electrons. Now keep in mind, protons have a positive charge and electrons have a negative charge. And what is this number 12? This is the atomic mass or the mass number. This one gives us the number of protons plus the number of neutrons. Now, as we think about atomic structure, remember we have our protons and neutrons are in the nucleus, and then the electrons are outside of the nucleus. In a neutral atom, the number of protons will equal the number of electrons. The number of neutrons can vary. So if we look at a few more symbols, here we have hydrogen, and we know based on the atomic number that we have one proton and we have one electron. And then focusing on the atomic mass, there are no more neutrons. So one proton, one electron, and 0 neutrons in this particular atom. Once again, with carbon, we know that we have 6 protons, 6 electrons, and 12 minus 6 gives us 6 neutrons. F is the symbol for fluorine, and we know that we have 9 protons and 9 electrons, and then 19 minus 9 tells us that we have 10 neutrons. So looking at these different symbols, we know which element we're talking about, and we can see how many protons and electrons, as well as how many protons plus neutrons we have. We need to remember that protons and neutrons are in the nucleus. Protons have a positive charge, neutrons no charge, and then electrons are outside of the nucleus with a negative charge. In a neutral atom, we're going to have the same number of protons and electrons. Now, if you look at a periodic table, rather than seeing the number 12, the atomic mass, you might see the number 12.01. We need to remember that atoms of a particular element can exist as different isotopes. So an isotope would have the same number of protons and the same number of electrons because we're talking about the same element. So of course that has to be the same. But a pair of isotopes will have a different number of neutrons. So for example, hydrogen exists as H1, H2, and H3. In the first case, we have no neutrons. Here we would have 1 neutron, and here we would have 2 neutrons. Carbon exists as C12, C13, and C14. Knowing that we have an atomic number of 6, that means in the first case we have 6 protons, 6 electrons, and 6 neutrons. In our second example, it's still 6 protons and 6 electrons, but now we have 7 neutrons. And in the third case, 6 protons, 6 electrons, but 8 neutrons. Now this number 12.01, the number that we see on the periodic table, This gives us the weighted average of all of the isotopes. So it takes into consideration the natural abundance of the different isotopes. So if we're talking about the number 1, the number 12, the number 19, this refers to a specific atom, whereas if we're looking at 12.01, this refers to all of the atoms, taking into consideration the natural abundance of different isotopes. So remember that our protons and neutrons are in the nucleus, but we need to focus on electrons. So in about the early 1900s, electrons were described as being both a particle and a wave, and this led to a better understanding of the electron. There are a few important concepts that I want you to consider. One of them is the Schrödinger equation, which looks like this. H psi is equal to E psi. This refers to the Hamiltonian. This is energy. And psi is called the wave function. So the Schrödinger equation describes the total energy of a system, and a system could be a particular atom. Now, there are many different energy levels, and each energy level is a solution to the Schrödinger equation. So let's just hang on to this idea of psi, the wave function. Another important concept is the Heisenberg uncertainty principle, and this tells us that it's impossible to know both the location and the momentum of a particle. So instead, we focus on probability. Where is a particle likely to be? And as we're thinking about probability, come back to this wave function, we use psi squared as the probability of finding an electron at a particular point in space. So when you take physical chemistry, you're going to get to love the Schrödinger equation. For now, all we need to focus on is that this wave function squared tells us the probability of finding an electron at a particular point in space. So let's think about where an electron might be. So we have our XYZ coordinates. Maybe an electron is likely to be here, or it could be here, or it could be here. Now, the darker, the more probable it is. So if this is the nucleus at the center, then it's very likely to find an electron close to the nucleus. It's much less likely to find an electron very far away from the nucleus. So if we plot all of those possibilities, then this gives us an electron cloud, right? This is all the possibilities of where that electron is likely to be. It's most intense closest to the nucleus, and then it gets lighter because it's less probable for the electrons to be further and further away. Now, from this cloud, we think about a boundary surface. We focus on a boundary surface that incorporates maybe a 95% chance of finding an electron within this space. So starting from all the possibilities graphed together, we then kind of simplify it and focus on this spherical shape. So this is an orbital. Consists of the possible places where the electron is likely to be. Notice we are talking about an orbital, not an orbit, right? So the electrons are not in a perfect orbit, not like the solar system. Instead, an electron is likely to exist in an orbital, which is a region of space where the electron is likely to be. Let's continue to think about orbitals. So remember, an orbital is a region of space where an electron is likely to be. Orbitals have shape, direction, and size. Now, the shape depends on the type of orbital. An s orbital is what we just saw on the previous slide, and here we have an overall spherical shape. We also have a p orbital. Now, a p orbital has a node, and a node is a region where there are no electrons, and these are opposite phase. So a p orbital has a node. It might be shown also more like this. There are also d orbitals, f orbitals, but in organic chemistry, we pretty much get to ignore them because we're going to focus on s and p. Next up, we can consider orbital direction. Now, with an s orbital, it's spherical, so we don't think about the direction. But with a p orbital, we can have it going in this direction, and this would be a px. It could go in this direction, py, or this direction, or this direction would be a pz. And finally, we can think about orbital size. These are both s orbitals, but this one might represent a 1s, whereas this one is a 2s orbital. The numbers 1 and 2, this refers to the principal quantum numbers. We can see that the 1s and the 2s have the same shape, but they're a different size, which means they have a different energy. Now, which one has a higher energy? Often we want to think about potential energy. If something is unstable, it's high energy, it's something, dangling off the edge of a high cliff, right? We want something that's close to the ground. Keep in mind that when we're talking about orbitals, we're talking about the region where electrons are likely to be. And in the very center, this is where we have our nucleus. So our nucleus with a positive charge compared to the orbital that contains our electrons with negative charge. So if we have electrons likely to be close to the nucleus, that is going to be more stable, which means it's going to be lower energy. If the electrons are held further away from the nucleus, that is going to be less stable or higher energy. As we continue to think about electrons, we want to focus on the electron configuration. We want to know how the electrons are organized. So let's start out with hydrogen. And how many electrons do we have in hydrogen? The atomic number is 1, so we know that there's 1 electron. Now, the electron configuration of hydrogen, we can write it as 1s1, where this is the principal quantum number. S tells us the type of orbital, and the superscript 1 tells us how many electrons are in this particular orbital. We can also think about an energy diagram, and we have energy increasing in the vertical direction, and the horizontal doesn't really have meaning. So this could be our 1s orbital, and we have 1 electron in there. Now we can use this or this to symbolize an electron because an electron has spin. With only 1 electron in this orbital, it's only 1 spin. Next, let's take a look at helium. So helium has 2 electrons, so the electron configuration is 1s2. And here we have our 1s orbital, and we have 2 electrons in the same orbital. Now we have to apply the Pauli exclusion principle, which tells us that 2 electrons in the same orbital must have opposite spin. Since there's only 2 options for spin, then the maximum is 2 electrons in an orbital. Next, if we look at lithium, this has 3 electrons. And so this will have the electron configuration 1s2, 2s1. So again, we've got energy going in this direction. If this represents the energy of the 1s orbital, then this would represent the energy of the 2s orbital. The 2s orbital is higher in energy because the electrons would be held further away from the nucleus. We have 2 electrons in the 1s orbital and 1 electron in the 2s orbital. And here we are using the Aufbau principle, which basically means build up. So the lower energy orbitals are filled before the higher energy orbitals are filled. Next, let's skip ahead to carbon, where we have 6 electrons. So here we have 1s2, 2s2, 2p2. So here is our 1s orbital, and then our 2s orbital, and then we have 3 two p orbitals. One of them is in the x direction, one is in the y, and one is the z direction. Now, the p orbitals, these are called degenerate orbitals, which is just a fancy word for saying they have the same energy as each other. So as we fill in our electrons, we build up. So the 1s is filled, and then the 2s is filled. And then we're going to have one electron in each of two p orbitals. And here we are looking at Hund's rule. So for orbitals with the same energy, the electrons spread out. Okay, so each orbital will get one before any one orbital gets two. So in other words, we could write this out a little bit more explicitly as 1s2, 2s2, 2px1, 2py1. Now, it doesn't matter whether it's x, y, or z. It's just that there are two of them that have one electron each. Hopefully this is all familiar to you and you remember doing electron configurations in general chemistry. Let's look at a few more examples of electron configuration. So we already saw helium, which has two electrons. So I'm only focusing on the atomic number. I'm not including the atomic mass because we only care about the electron configuration, not which particular isotope we're talking about. So with helium, we have two electrons. So the electron configuration is 1s2. So if this is our energy diagram, here is our 1s orbital, and it has two electrons. Our next example, neon, we have 10 electrons. So this will have the electron configuration 1s2, 2s2, 2p6. So here's our 1s, 2s, 2p, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the third example, argon, we have 18 electrons. So 1s2, 2s2, 2p6, 3s2, 3p6. Here's our 1s, 2s, 2p, 3s, 3p. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. What you should notice is for all three of these noble gases, all of the orbitals are completely filled. All of the orbitals are completely filled. So the noble gases are also called the inert gases. They're not reactive to form compounds because they're already stable. So what we see is that elements have a special stability when the orbitals are completely filled. Before we start thinking about compounds, there's one more aspect of atomic structure that I want you to consider, and that is the valence electrons. With valence electrons, we're talking about electrons in the outermost shell of any particular atom. So for carbon, we have the electron configuration 1s2, 2s2, 2p2. So we've got 1 versus 2. So we have 4 valence electrons in carbon. If we're looking at chlorine, this is 1s2, 2s2, 2p6, 3s2, 3p5. So we've got the 1 shell, the 2 shell, the 3 shell. So these are our valence electrons. So in chlorine, we have 7 valence electrons. As we're learning about organic chemistry, do we always have to consider all of the electrons? No. We're going to focus on the valence electrons. The inner electrons, these are buried deep enough that they're not going to be involved in reactions. We want to understand organic chemistry so that we can understand the reactions that organic compounds undergo. So we're just focusing on the electrons that are in the outermost shell because that's where the reaction happens. So usually we do not consider all of the electrons, we just focus on the valence electrons. So When we want to study the valence electrons, all we have to do is write out the entire electron configuration and then figure out the highest principal quantum number, add up the number of electrons within those orbitals, and that brings us to 4. We write out the whole electron configuration, find our highest principal quantum number. Here we have 5 plus 2 is 7, and that's a pretty tedious way to figure out the valence electrons. Fortunately, the easy way to do it is to look at the group number on the periodic table. So we can easily see how many valence electrons we have, and we don't have to go through the entire electron configuration. It's good to have a little practice to make sure that you still remember how to do it, but we don't have to go through this every time we're thinking about an atom. So as we close out our brief review of atomic structure, remember we want to think about the nucleus compared to the electrons. In the nucleus, we are talking about protons, which have a positive charge, and neutrons, which have no charge. And we also have to be aware of the fact that there are isotopes, which would be different atoms of a particular element that have a different number of neutrons. We also have to think about electrons. So remember, electrons exist in orbitals, and this is the region of space where electrons are likely to be, because we're thinking about the probability of finding them within a particular space. And with orbitals, they have size, they have shape, and for some of them, they have direction. When we think about the electron configuration, this describes the organization of electrons in an atom. How many electrons are in which orbitals? As we think about the noble gases, remember that these all have full orbitals, and this gives them a special stability, which we're going to see why that's important as we start talking about bonding in our next topic. And the last concept I want you to keep in mind regarding electrons is that we are going to focus on the valence electrons, so the outermost shell of electrons. Hopefully this was sufficient to dust off those cobwebs so that you remember the important aspects of atomic structure so that we can build on that as we start thinking about compounds.